We knew Rocky World's discussions as the epitome of professionalism. Here we are. Yeah, okay, we're on the hour. I think we might as well get started. So it is, as always, great to see you all here. And we welcome Laura Schaefer from Stanford, who joins us today to continue our Rocky Worlds discussion series. So as a reminder of the netiquette, we encourage you to use your full name on the Zoom. Please keep muted throughout the talk. And when you ask questions at the end, please do turn on your video so we can see you. And I'll now hand over to Laura to talk to us about planetary redox.
Great. Thank you, Claire and Anjali, for the invitation to join the Rocky World discussion. I was mentioning earlier, this is usually happening a little too early for me in California, so I appreciate the flexibility and the timing. So today I want to talk a little bit about some work that my group has been doing looking at redox gradients that might develop in planetary systems using planet formation simulations. And I know that redox and oxygen fugacity is a concept that has really started to become relatively common in exoplanet talks, especially people thinking about magma oceans or atmosphere formation. But not everybody has heard about it. So I'm going to start off with a brief overview about what I mean by redox and oxygen fugacity, just so that everybody is a little bit more comfortable with those concepts. So when we say redox, it's reduction and oxidation reactions, and we're thinking about the different oxidation states of different elements that are present in the mantle rocks of a rocky planet. Most elements have sort of a single oxidation state that they prefer to take, like magnesium and calcium are always sort of 2+, and alkalis are always 1+. But many of the transition elements can take multiple different oxidation states or charges in their bonding with oxygen. And this is just showing some of the common oxidation states for some of the abundant elements. And the one that we're mostly concerned with right now is iron. In the environment of a rocky planet, iron can take 3 major oxidation states. That's 0 when it is in the metal phase. It's 2+ in most silicate minerals. And then a small portion of iron in the silicate mantle of the Earth is in the form of iron 3+. And this just dictates essentially how much oxygen that iron can bond with in the very oxygen-rich environment of a silicate planet. And this is showing sort of the relationship between the oxidation states of iron and oxygen fugacity. So oxygen fugacity here is shown relative to a buffer that I'm going to show on the next slide, the iron westsite buffer. And that is shown sort of by this vertical bar here. And to the left, or at lower oxygen fugacities, iron is going to be almost entirely in the metal phase. To the right, it's going to be mostly in the iron 2+ oxidation state. And then once you get up to higher oxygen fugacities, iron will be mostly in the iron 3+ state. In Earth's mantle, we are around this oxygen fugacity, around QFM. And so we have a mixture of iron 2+ and 3+. There's only a relatively small amount of iron 3+, about 2 to 6% or so in the Earth's mantle, and most of it is in iron 2+. So the reason we care about this, and I care about this in terms of thinking about the early atmosphere formation, is that the oxygen fugacity of the mantle dictates the composition of gases that are emitted from the mantle during planetary outgassing. And that's sort of shown in this slide, where we're showing the relationship between oxygen fugacity, which is correlated with those oxidation states of the iron, and these gas reactions. Oxygen fugacity for the gases, you can think of just as the partial pressure of oxygen in the gas, and then the abundances of the gases are just related directly to the oxygen fugacity. So for instance, the ratio of water to hydrogen in an outgassing system is directly proportional to the oxygen fugacity. And the same is true for carbon dioxide and carbon monoxide. Buffers are essentially where we have minerals present in a system that are at equilibrium, and they are related by a reaction that includes oxygen, and so that fixes oxygen at that particular value dictated by the equilibrium of that particular reaction when, say, these three minerals are coexisting, quartz, phalite, and magnetite. It would fix the oxygen fugacity to fall along the reaction line. Looking over at the figure over here, that reaction line is shown by this line labeled QFM. And what we're seeing on the y-axis is the oxygen fugacity and temperature here on the x-axis, or 1 over temperature. So in temperature space, these oxygen fugacity buffers are approximately parallel to each other. And so we use them as sort of fixed reference points in space, in oxygen fugacity space to refer to, rather than just saying I have an oxygen fugacity of -20, I would say I'm at this particular temperature, I'm at the iron wustite buffer. And because that buffer system tells me that these minerals are coexisting, I now know that there's both metal and iron 2+ present in that particular system. So that's use of buffers here. So the two I'm going to refer to are the two reactions I'm showing here, iron wustite and quartz phalite magnetite. I'm mostly going to be focusing on the iron wustite, where we do have metal present in our system, so relatively reducing conditions and low oxygen fugacity. Now, in the inner solar system, if we look at the terrestrial planets in the inner solar system, it looks like there is an oxidation state gradient in the inner solar system. And that is shown in this diagram from a paper from 2019 that looked at the mantle and core compositions of the terrestrial planets in the solar system. And what it looks like is that the mantle abundance of iron 2+ FeO correlates with the metal fraction in the iron fraction in the metallic core, where we have Mercury being the most reduced with the largest core fraction and the lowest mantle iron abundance. Earth and Venus being somewhat moderate, and then Mars and Vesta being much more oxidized with smaller cores and larger amounts of iron in the mantle. And so this looks like a chemical gradient, right, that might have been existing within the protoplanetary disk out of which the planets of our solar system formed. And so some models have suggested that there was this redox gradient in the planetesimal disk. And it's been suggested that in order to match the composition of Earth's mantle and core, the trace element chemistry, you need some kind of compositional gradient across the solar system. And so one thing I want to also distinguish when we're talking about this is the difference between the bulk oxygen fugacity and the mantle oxygen fugacity. The bulk oxygen fugacity is just looking at the composition of the entire planet, so that includes both mantle and core. And it looks at basically the ratio of the iron 2+ in the mantle to the total amount of iron in the core. So iron and metal divided by, the FeO in the rock divided by the iron in the metal. And this gives us a bulk oxygen fugacity relative to the iron wustite buffer from this little equation here. So Earth's bulk oxygen fugacity is around iron wustite -2, and Mars is a little bit more oxidized, so it's iron wustite -1. It's a slightly more oxidized. And then for the mantle oxygen fugacity, this is where we're looking at the silicate rock as an isolated system without considering the composition of the core. And this is the oxygen fugacity that dictates the outgassing composition from mantle gases. And this is going to be given by the relative abundances of iron 2 plus and iron 3 plus in the silicate phase. And I mentioned that Earth's upper mantle is close to that QFM buffer, which again, because the buffers are relatively parallel to each other, QFM is equivalent to iron wesite plus 4 or 5, depending on your temperature. So Earth's upper mantle is around iron wesite plus 4, right? Whereas the bulk oxygen fugacity of Earth is around iron wesite minus 2. Mars's upper mantle is a little less oxidized than Earth's, is around iron wesite plus 2. And this is found from empirical relationships that people have developed for silicate minerals, where you just take the silicate system and you measure the iron 3 plus to iron 2 plus abundance and correlate that with oxygen fugacity. And that is a function of both pressure, temperature, and the bulk composition of the system. The mantle oxygen fugacity then is what is controlling the composition of outgassing, and outgassing fluxes of different gases are going to depend on this oxygen fugacity of the upper mantle. Again, Earth is around the FNQ or QFM buffer. People write this in different ways. And so the upper mantle of the Earth is right around this FMQ buffer. And in this case, the amount of iron 3 plus in the upper mantle, again, relative to the iron 2 plus is around 2 to 6% in the upper mantle. And one thing we have determined from looking at some older samples of silicates on the Earth is that Earth's mantle oxygen fugacity has been relatively constant for most of recorded geologic history. So we're at the FMQ or QFM buffer right now at the present day, and people have measured oxygen fugacity going back to about 3.5 billion years in different samples of mid-ocean ridge basalts. And I've found that it is relatively consistent with present day oxygen fugacity. Whereas we know from core formation models that when metal is reacting with the mantle, that the oxygen fugacity must have been much lower, well below the iron wesite buffer. We also have samples of zircons from about 4 billion years. They give quite a spread of oxygen fugacities, which are somewhat consistent with present day, but could have allowed for some decrease back in the Hadean. And there's a small indication of a small oxidation change in the Earth's mantle around the early Archean. I've got recent results. This is I'm realizing not so recent anymore, 2016, almost 10 years now. But some work has shown that there is a small decrease in the mantle oxygen fugacity of about 1 log unit. So not compensating for the entire change from core formation to present day, but some overall change in the oxygen fugacity of the Earth's mantle over time, just a slight one. The Martian mantle oxygen fugacity is less well constrained. It seems to be a little bit lower than Earth's upper mantle. And these have largely been measured from Martian meteorites. So on this figure on the left, we have terrestrial samples from the Earth showing this is the Hawaii volcano, mid-ocean ridge basalts, and showing that we have oxygen fugacities around the QFM buffer, whereas the Martian meteorites are 2 to 4 log units lower than that in oxygen fugacity. A more recent study has looked at this again and has found, again, here's a comparison between Earth samples and Shergotite's Martian meteorites that has found that around FMQ minus 2. So about 2 log units lower than the Earth's oxygen fugacity. So while the bulk oxygen fugacity of Mars is a little bit higher than Earth, the mantle oxygen fugacity is a little bit lower. In contrast, for Mercury, the oxidation state of magmas on Mercury has been estimated based on the abundance of FeO in the silicates, as well as the presence of some really reducing sulfides like calcium sulfide and magnesium sulfide that were observed with the MESSENGER mission to Mercury. And the composition of the surface appears to be relatively similar to instantite chondrites, suggesting a very low oxidation state. So the redox states for magmas on Mercury have been suggested to be around iron voesite -4 to -7. So extremely reduced in comparison to both Earth and Mars. This is a compilation from a review paper looking at different samples from chondrites to achondrites, Mercury, the Moon, Mars, Venus, and Earth, and looking at the recorded oxygen fugacities. Again, the bulk oxygen fugacities are recorded here mostly by the primitive mantle, whereas other samples here are more representative of the mantle oxygen fugacity. We can see that there's quite a range, but again, we have Mercury being very reduced, and Earth and Mars and Venus being much more oxidized. So this is all suggesting, right, that we have this bulk oxygen fugacity gradient in the solar system, but the mantle oxygen fugacity doesn't necessarily seem to correlate either with distance of the planet from the sun. And so one of the things that we wanted to ask in looking at some planet formation simulations is, do all planetary systems record the primordial bulk oxygen fugacity gradient? And are there mantle redox gradients that also exist within planetary systems? And we're going to do this by looking at some models of planet formation that include the process of core formation and equilibration between metal and silicate. And in order to determine the mantle oxygen fugacity, one thing we have to be able to compute is the iron 3+ abundance that would exist immediately after core formation. And this has only become possible relatively recently with new thermodynamic data that's available for silicates. It used to be that people thought that there was no iron 3+ in the Earth's mantle at the end of the planet formation process, that Earth started only with metal and iron 2+, and there is essentially no iron 3+ left. But we've since discovered that there's a number of ways that you can make iron 3+ during the planet formation process. One is by essentially oxidation of the mantle by the atmosphere through a magma ocean. The one I'm going to talk about, though, is by a high pressure reaction called the iron disproportionation reaction, where at high pressure, the iron 2+ actually disproportionates and makes 1 atom of metal and 2 atoms of iron 3+. If this happens at a time when that metal can separate out of the mantle into the core, then this results in a net oxidation of the mantle. Mark Hirschman looked at this for a number of previous models of core formation for the Earth and calculated some potential iron 3+ abundances in the Earth's mantle at the end of core formation. Each of these different pressures and points is a different model of core formation. And he found that he could definitely match or even exceed the amount of iron 3+ that we have today. For Mars, we then also end up with some non-zero iron 3+ abundances. The problem, though, with trying to do this rigorously is that the thermodynamics of the system is still developing. This is a comparison figure from the most recent paper on this problem, looking at the ratio of iron 3+ in a silicate as a function of pressure for different thermodynamic models. Until this paper came out, the 2 models we had were a first principles dynamic simulation from Ji Deng in this blue, and then experimental work over here by Kat Armstrong in the gray. And you can see that they give wildly different iron 3+ abundances as you go to high pressure. And the Armstrong model, in fact, basically would say that at the conditions of Earth's core mantle boundary, all iron would be iron 3 plus. So that one didn't extrapolate well. The Zhang model that I'll be using in this particular model is shown in the red curve, right? So we can now see that as we go to higher pressure, the iron 3 plus abundance does in fact increase, but it's not blowing up. So the model that I'm using throughout the results I'm going to show you next is using a model of metal-silicate equilibration. This is based on models that have been done for Earth's mantle to try to match the trace element abundances in Earth's mantle. There's a long history of this from many people who have looked at this going back to the 1970s. But this is based on some updated partition coefficients where we're looking at the reaction of iron metal as it is being delivered to the planet, reacting with silicates. Some silicon and some oxygen will go into the metallic core, and the chemistry of that is dictated by these partition coefficients, for which there are these lovely complicated expressions that depend on the composition of the system. The ones I'm using here are from Rebecca Fisher's work for silicon and oxygen. And then, of course, we add in the disproportionation reaction in order to be able to compute the iron 3 plus abundance at the end of the as a result of these core forming reactions. And for the purposes of this model, we assume that all of the metal that is formed in this reaction does in fact join the core. So it is fully removed from the silicate system. And for this, I am using these particular sources for the thermodynamic data. Now, just a little bit of background on the planetary simulations. For this particular model, what we're going to be looking at is the TRAPPIST-1 system, which most people are familiar with, the system of 7 planets. This is looking at the joint inversion that Eric Egel did back in 2021 to constrain both core mass fractions and water mass fractions. And we can see that there is, in fact, a plausible gradient in the core mass fraction for this planetary system as a function of orbital period. It's very slight. It is not as extreme as the difference between Mercury and Mars in our solar system. But there is a hint of a gradient in core mass fraction. This could also equally be well explained by an inverse gradient in volatile abundances because of the degeneracies inherent in mass radius models. So the models do not do a good job of distinguishing between volatile poor and volatile rich versions for a couple of these planets like E and F. G and H are probably pretty volatile rich, being outside of the habitable zone. So we wanted to look at this, the TRAPPIST-1 system. And for this project, I'm using some simulations of the local formation of the TRAPPIST-1 systems from Matt Clement. This is a subset of the simulations he published in his 2024 paper, where the TRAPPIST-1 planets are all forming in situ. And so we have about 22 simulations that we're looking at, and each of these simulations produces 7 planets. And the planets range in size from about 0.2 to almost 3 Earth masses. And we run this metal-silicate equilibration model on all of these simulations, taking into account the different impact history for each of these objects. And this is similar to work that has been done in the solar system by Ruby for looking at the Earth formation. Where what we're doing for the planetesimals is we're assuming a redox gradient in the planetesimal disk. So in Ruby's models for Earth, they had some simulations where they just left the composition constant, and some in which they had a step model where there was an inner region that was more reduced and an outer region that was more oxidized. And so here's the compositions for the planetesimal disk that I'm going to be using here. Apologies, these are a little confusing. So for this particular talk, I'm just going to show some simulations that have a constant core mass fraction in all of the planetesimals in the initial disk. We do have a gradient in water mass fraction with the lowest values interior to the habitable zone. We have a value of about 0.1% within the habitable zone, and then slightly higher as we go outward beyond the snow line. So that's core mass fraction and water mass fraction over here. And then the blue curve on this right-hand figure is showing the gradient that we're taking for the iron oxide in the mantles of these planetesimals. We, again, sort of follow the water mass fraction gradient. We have a low value in the inner system interior to the habitable zone, about 10% within the habitable zone, and higher as we move further outward. And we take a corresponding reverse gradient in the metal composition, where in the reducing inner disk, we assume that there's some silicon in the metal, and then no silicon in the metal as we move further out. So then what we do is we simulate each of the, calculate the equilibrium as each of the impacts occurs. This is just showing a one of those 22 simulations where we get 7 planets, and you can see the growth histories of these planets over time. Sometimes we have small growth increments for the small planetesimals. Sometimes we have embryo collisions, and we get a large mass jump. And then this is showing how the iron 3+ abundance is growing as a function of the mass accretion. Some of the preliminary work here has been done by my grad student Chase Alvarado Anderson, and he's continuing to add volatiles into this model. So what we find for the bulk oxygen fugacity in these systems is, what I'm comparing here is models in which I'm taking that step gradient on the right-hand panel for the iron oxide abundance in the mantle, and on the left, I'm just assuming a constant iron oxide abundance throughout the simulation. When we have no gradient, we don't really see any difference in bulk oxygen fugacity as a function of semi-major axis for the planets formed in this system. This is all the planets formed from all of those simulations, just shown on a single plot here. When we do take that step gradient, we see that there is a bit of a gradient in the bulk oxygen fugacity of the system, where we would expect more reducing bodies interior to habitable zone and more oxidized bodies from the inner habitable zone edge moving outwards. And so this bulk redox gradient really seems to depend on the sharpness of the gradient within the disk. And there's no significant dependence that we've found so far on the core mass fraction or the bulk density on the semi-major axis. The mantle oxygen fugacity or mantle redox state, the proportion of iron 3+ to iron 2+ in the mantle, doesn't seem to depend on the semi-major axis. So it doesn't depend on where the planet formed. What we see is kind of a scatter here for both the simulations that had a gradient in FeO and those that did not. And what we get is we get a cluster of small planets that form in the inner system and another cluster of small planets that form the outer system. And these objects, we get most of the large planets forming with the high iron 3+ abundance in this inner region here. Again, the mantle redox is given by this relationship and its comparison to the oxygen fugacity. And so there's no corresponding trend in mantle redox with semi-major axis to the bulk redox gradient. What we find instead is that the mantle redox depends on the planet mass. We find that if we have this step gradient in FeO, we get a slightly broader spread, a little bit more scatter. to the final mantle iron 3+ abundance, but it's still a pretty clear trend in planet mass. So the mantle redox follows the planet mass, and this suggests really that larger planets would be more oxidized. So that's sort of the preliminary results for these simulations. And the things that we're working on next are to add volatiles into this model to see how those will modify the redox. So in particular, we're looking at the partitioning of hydrogen, carbon, and nitrogen between the core, mantle, and atmosphere. We'll plan to include hydrogen escape because one thing that has been shown in the past is that the removal of hydrogen from an atmosphere is a pretty effective and efficient oxidant for a planet. So this figure is showing that adding water to a mantle has much less of an effect on the oxygen fugacity than removing hydrogen from our planet would. So that's another process that we're planning on adding. We are also looking at simulations using the same impact history, but different initial core mass fraction distributions to see how that changes both the bulk oxygen fugacity of our planets, our final planets, and the mantle redox. The other thing that we're then planning to look at then is the atmospheric history of these planets by looking at mantle outgassing models. Some of this work is being done by Ginelli Perez at Johns Hopkins, where we have some models that compute the deep volatile cycles of water and carbon and nitrogen, where we are looking at, once these planets are fully formed, how do these volatiles exchange between the interior and the surface of the planet over long timescales, and how is that affected by the tectonics of the system? So Ginelli is working on a paper that's in prep and is just about ready to get submitted, where we're looking at the effect of oxygen fugacity on the outgassing history of the TRAPPIST-1 planets. And what she has found is that we do see differences, but they're not as stark as you might expect based on simple oxygen fugacity calculations because of some of the secondary processes that happen, like hydrogen escape and the oxidation of carbon monoxide to CO2. So even at low oxygen fugacities, very low oxygen fugacities, while we do get a lot of hydrogen in the atmosphere, we never find carbon monoxide to be a very prominent gas, for instance. Whereas at high oxygen fugacities, we're expecting atmospheres mostly dominated by CO2, as you might expect. So I think that there's a lot of problems in this sector for thinking about the atmosphere interior evolution of different rocky planets. We're trying to start in a holistic sense from the early time period, from core and mantle equilibration, to see how that sets the oxygen fugacity of the mantle, and then look at how that is going to evolve over time and how the role that plays in affecting the atmosphere over long time scales. Just to conclude here, I'll say that we've been looking at these planet formation simulations to try to get an estimate of whether the bulk redox gradient that we see in the solar system is a feature that we should expect to see in other planetary systems. And it really depends in these initial simulations on the sharpness of the initial redox gradient, and sometimes we just see sort of a scatter in the bulk oxygen fugacity. And the mantle redox does seem to depend strongly on planetary mass. It depends really strongly on the pressure of metal-silicate equilibration to set this initial iron 3+ abundance. And so, we're considering other processes as we move forward, including volatile reactions and how those can modify the mantle redox states of planets both in the solar system and outside the solar system. So I think I'm gonna stop there, and I think I've left plenty of time for a discussion and questions here. So thank you all.
Thank you so much, Laura. That was excellent. I'm sure we have some questions. I see Tad. Or no, sorry, this is clapping. This is clapping. This is not questions. Does anyone want to raise their hand? Uh, okay. If not, I actually may be able to take the liberty of asking the first question. Okay, so in your model, you are showing that you find no effect of semi-major axis on the mantle Fe3 plus to Fe2 ratio. I'm wondering if there's anything that goes into the model that you could conceive of actually leading to this result, because you say that you don't include like hydrogen escape, for example.
Yeah. So I could see that you would. I think there's probably some confounding effects here, right? Once you include the atmosphere and you include hydrogen escape, then distance from the star is going to play a role in that. I would say that's probably less tied to the initial planetesimal, anything happening within the initial planetesimal disk, right? So not a direct probe of planetesimal composition across the disk. But yeah, I do think that you will find that there are going to be these processes like hydrogen escape or oxidation of the mantle from the effect of water in the steam atmosphere losing the hydrogen and keeping the oxygen. All right, that is definitely going to confound some of these effects. And of course, there's going to be some differences there because that is also a mass dependent process, right? So you would expect less of that to happen for more massive planets, but more of it to happen for closer in planets. So there's going to be some differences there. Yeah.
Oh, yeah, I'm excited to see where this leads to when you end up kind of trying to model it.
Yeah.
Um, yeah, I'll take some questions from the room. Okay, Tad, round two. Here you go.
Okay, thanks. Yeah, you called on me, so I figured I should ask a question. Great talk as
Hi,
usual.
Ted.
Hi. So you discussed the TRAPPIST-1 like volatile inferences from Agel et al. Earlier on, and I realized I wonder have you considered or have people considered maybe like taking into account these JWST inferences of a potential lack of atmospheres on certain TRAPPIST-1 planets? And is there any way to use that to better understand the interiors? Like if we know that there's insufficient outgassing to replenish the atmosphere, does that then lead to an extra constraint on the FO2 of the interior in any way?
Um, so far, I don't think it's constraining enough to make those kind of inferences for most of these planets. So I think, for the inner planets where we have the strongest constraints, we expect them to start with low volatile abundances in the first place. And so the fact that they haven't managed to maintain an atmosphere wouldn't be super surprising. So yeah, I don't think the constraints are really strong enough to make those inferences yet. But hopefully in the future, maybe we'll be able to do that. Yeah.
Makes sense. Thanks.
Okay, so I see. I'm sorry, I don't know which is your first name and your last name, but Gabriel Nathan is
Gabriel.
what.
Hi, yeah, it's Gabriel. I got two first names. Um, so you showed that there wasn't this connection between semi-major axis and redox state of the mantle, but there was this correlation between the size. And I noticed that some of the planets that were in the middle were very large Fe3. So was that larger planets in the middle of these simulations appearing? And then with that, I assume if they're in the middle of this redox gradient that you've set up, they're going to be built from more heterogeneous material. So would that mean that like an Fe3 plus signature is tied to heterogeneous material creating, or is it purely tied to the planetary mass? And thanks for the talk. It was great.
Yeah, so what we're finding, at least so far, is that so in these particular simulations, the biggest planets are formed sort of in the middle of our semi-major axis range. So we have smaller planets interior and smaller planets exterior. And so that's a good portion of the effect that we're seeing, and we are seeing a relatively consistent spread in iron 3+ abundances as a function of planet mass, which is sort of related to the history of the growth. So you get sort of a plus or minus 5 to 10% iron 3+ for any given planet mass around some central value. That spread is a little bit bigger depending on the FeO gradient in the disk. So the other thing that we're looking at right now is some simulations where we've basically taken the same accretion history, but changed the initial core mass fraction distribution in those planetesimals. And that is having, so in that way, we're getting a little bit more heterogeneous accretion effects across the whole simulation. And we're still seeing this strong mass dependence for the mantle redox effect. It does, again, introduce a little bit more scatter, but it does not produce a strong semi-major axis dependence.
Thanks.
I see Angeli has her hands up.
Yeah, so I see there's a question in the chat, so I'll read that one out first,
Sure.
and then I'll ask my question afterwards. So this is a question from Harrison Nichols, which is, if FO2 doesn't depend on separation, but does correlate with planet mass, what does this say about larger planets which have reducing atmospheres, for example, K218b?
Okay, yeah, so K218b I think is probably a different class of planet than what we're simulating here, right? It's got a hydrogen-dominated atmosphere, and we're not including right now really any atmosphere effects on the mantle chemistry, and we are not including an accreted gas envelope. So I do think anytime you accrete a significant amount of hydrogen, your planet's automatically a lot more reduced. You just are reducing sort of the bulk hydrogen to oxygen ratio by moles. That's a significant effect with even a very small amount of hydrogen by mass. So yeah, so there's definitely this effect, right, that the hydrogen envelope is going to have. That is not something that these particular simulations can currently take into account. Yeah.
Thanks. So my question after that is, I'm really excited about what you were saying about the volatiles that are sort of coming up, and it's clear that mass and the mass as a parameter seems to be something that's really driving the overall oxidation state. So I was wondering, do you have a prediction for how much volatiles will be able to imprint on that, and would you need to accrete like actually quite a large amount of volatiles to make any difference?
Let's see. No, I don't think you have to have a crazy amount of volatiles to make a difference here. Yeah, especially if for considering the effect of like loss of hydrogen from water, that 1 mole of oxygen can get you 2 moles of iron 3+, right? So the mantle mass is big, so you do have to have a reasonable amount of water to affect that bulk composition significantly. But it's not like you don't need 50% water by mass, right, to do this. It's reasonable volatile abundances. Yeah. Yeah.
Sorry, okay. Hannah?
Hi, thanks. It was a really interesting talk. As a planetesimal person, I was just wondering if you'd mind re-explaining again what you're saying about you showed some simulations and now you're saying you've done the ones with the variable core mass fraction. Are you saying
Yeah,
the ones
sorry, I'm saying
weren't differentiated, or what do you mean by the variable core mass fraction compared to the previous gradient in redox? Was one like a bulk, just undifferentiated material, and one's differentiated, or what's changed?
Yeah, so I keep saying planetesimals. These are all probably well, okay. So the smallest is like 0.005 Earth masses.
Okay.
So they're reasonably large, and so we're assuming that they are all differentiated initially. So there are a handful of embryos that the simulation starts with. And the planetesimal disk, I think, or this original disk of objects goes from like 0.02 up to 0.1 AU. And so the simulation initially has taken just a constant core mass fraction assumption for all of those objects in the original disk. And what we're changing in the future simulations that we're working on right now is essentially setting up different gradients in the core mass fraction of those objects. So either they start off all with like 30% core mass fraction, or we start with higher core mass fraction interior to the habitable zone and lower exterior, or a linear gradient in those objects. So yeah, so we're assuming that everything has already differentiated ahead of the start of this simulation.
And so in the first simulations, the gradient you were imposing was just in the mantle redox?
That's right. Yeah.
Okay.
Yeah. Yeah.
Cool. Thanks.
Okay, maybe I can ask my own question if that's okay again. Okay, so when we talk about this dependence on Fe3 plus Fe total on the planet mass, I think in my understanding, what we're really talking about is the dependence on the pressure of the last metal-silicate equilibration. Is it that, or is there really like a mass dependence?
No, you're right. It is the pressure at which that reaction is happening.
Yeah. So what I'm wondering is like, is this, do we know that this is a good assumption that this pressure is always kind of like relatively in the same place as the mass of the planet goes up? Or is there a way to test this somehow?
What we're assuming is you're right. There's a fair amount of assumptions happening here. So I didn't talk too much about the mechanics of the simulation. So what we do is for every impact in the simulation, we calculate a rough amount of melt that occurs within the mantle. And we assume that the impactor is equilibrating with that melt within the mantle. So it's not equilibrating with the whole planetary embryo, just the portion that melts. So sometimes it's the whole object, sometimes it's just a small portion of the mantle that it reacts with. So there is only partial equilibration happening. And when that happens, we take the equilibrium pressure for the metal-silicate reactions as the base of that melt layer. When it is the whole object that melts, we take some fraction of the embryo's core mantle boundary pressure. It's not the full depth, because if we did that, essentially everything would turn into iron 3 plus. So it is a fraction. It's about 50% of the CMB pressure. I am finding that these simulations are currently over predicting iron 3 plus for one Earth mass planet at that equilibration pressure range. So in order to match a one Earth mass planet, I actually have to reduce that down to about 30% of the CMB pressure. People have done this a lot for studying Earth, and in particular for trying to match all of the trace elements that should be in the core that have residual abundances in Earth's mantle. And they find that by trying to match, 10 trace elements at a time and looking at the pressure dependencies of the partition coefficients and the redox dependencies and so forth, you get a pressure constraint that is somewhere in that range, somewhere between 30 to 50% of the CMB pressure. So a little hand wavy, but yeah, that's what we're doing right now.
Yeah, I was just wondering if there's any avenues towards constraining this as like a kind of universal fraction of the planet.
Yeah, I don't know if it can be universal, right? It's probably always going to depend on the particulars of the impact that happens, right? The velocity of the impact, the temperature that you reach within the melt pool, and the different fractions of material that equilibrate, right? That's going to dictate the amount of time everything has to equilibrate together. And yeah, so having, I think, maybe some additional simulations, people working on in particular giant impact simulations and trying to constrain the separation of the fluids, right? The separation of the metallic fluid from the silicate fluid. That would start to help us in incorporating those kind of results in a parameterized way into these formation simulations, I think would be the way to go. Yeah.
Cool. Okay, I'm gonna take another question from Angeli.
So I think there are a few in the chat, and I see that Eric has to go soon, so I'm gonna read out that question first. So Eric has asked, one thing that's frustrating about TRAPPIST-1 is that we don't have constraints on the iron to magnesium to silicon ratios of the host star. Have you examined the influence of refractory ratios on your results?
I haven't yet. At the moment, we're just assuming sort of solar-like compositions. That is something that I would like to look at. I don't know that it is going to affect things as much as the gradients that we're imposing in the disk would. So it's something that we can play around with. I think having sort of like a constant iron to magnesium to silicon ratio throughout the disk is probably the most important assumption, and what that ratio is would dictate sort of the bulk mantle to core compositions that you might be able to get, but wouldn't, I think, change the trends that we're seeing. So yeah, one thing I didn't emphasize, I don't take any of the absolute values that I have said at face value for any of this, right? It's the trends we're looking at that are important. It's not the absolute value.
Yeah, if we have time for one more, there are so many questions in the chat. I might read out another one. So from Tiff Barry, from your results and any estimate of mantle FO2 for Mercury, can you say anything about whether you think Mercury had once been a larger planet?
It's an interesting question. I don't. It's a very weird system in the solar system. We see a lot of sulfides on the surface. A lot of really reducing. There's some metal present on the surface, right? Not very much FeO in the silicate. Magnesium and calcium and sulfide. It's a very reduced system. So can I say if it was a larger planet ever? I don't really think I could say that from the current chemistry. So if it was a larger planet and it lost a significant chunk of mantle, that would have come with a certain amount of re-equilibration of the system, which I think is probably what we're seeing. So there, other people who have thought more deeply about Mercury might have thoughts on this, but at the moment I can't think of whether I could say that or not.
We maybe have time for one more. What do you think, Claire?
Yeah.
So there's another question from Gabriel. Is it reasonable for a redox gradient to exist in such a small semi-major axis space as exists in the TRAPPIST-1 system? Here we're talking about several planets forming within a fraction of the inner solar system. It seems difficult to have any redox difference in such a small space, especially given mixing between planetesimals once impacts occur.
It is a very small space, right? But it is within we are looking at objects within the range of the snow line, right? So that is sort of well, right now we're taking habitable zone, but it's relatively close to the snow line. So the volatile gradient is sort of what we're using to establish where to assign the iron gradients. So yeah, it is a very compact system. So it's possible that it's too small. We are also looking at some solar system simulations right now as well, so that we can see if we're matching the solar system gradient as well.
Oh, I think we have one more from R. Mark Elowitz.
Mhm.
We can go through this one. So maybe I will read it out unless R. or Mark, you want to do it yourself if you're here. Okay, so assuming.
Hi. Yes.
You,
Yeah, I could go ahead and read it out. Yeah. I'm assuming that if Earth, Moon are outliers on the solar system's oxygen fugacity plot, the redox trend, they seem to be outliers. So I'm assuming they have completely different oxidation states. Does that mean that Theia itself, the impactor, came from a completely different zone in the solar system and not close proximity to Earth itself?
So Moon by itself is a considerable outlier because it's mostly made out of Earth mantle material. So it doesn't have a very big core. It's got a very, very small core. And so that's why the Moon itself is an outlier. And I think this is also why the Earth is not falling directly on that line, is if you added the Moon back in, it would fall pretty close to that line. So I don't think that there's significant evidence that the Earth Moon system is considerably outside of this gradient, right? And we might not expect like a perfect gradient to exist anyway. Some scatter should be reasonable, given the stochastic nature of everything. But everything we sort of know about isotopic compositions and things suggest that the Earth and Theia were probably pretty, at least isotopically similar initially, or at least not crazy different. And so that would suggest that they are sort of coming from similar regions in the protoplanetary disk. And then I would assume had similar redox.
Thanks.
Great. Do we have any final questions? Okay. Okay, Kirsten, go ahead.
Hi, Laura. Great
Hi,
talk.
Kirsten.
My question is actually more of a practical question, and I'm doing something that's slightly relevant, and I would love to cite your work. Do you know like a time frame of when you'll be putting this out in paper form for us to cite?
Sure. Hopefully sometime in the next month or two.
Great, thanks.
Hey, you heard it here first on Rocket World's discussions. This paper is submitted next month. I'm excited. Okay. Unless there's any more last minute questions, I think let's all give Laura another virtual round of applause. That was fantastic. And we're looking forward to seeing you here in October, where we're going to have Kazuma give a talk about atmosphere observations. And thank you all. Have a wonderful rest of your Thursday and see you next month.